For any integer m and any real number x, if x is not an integer, then the floor of x plus the floor of m minus x equals m minus 1. Let's prove this. Let's first define n. N is going to be the floor of x, and let the fractional part of x, that's the curly brace x, that's just going to be x minus the floor of x. So you can think of the fractional part as like a decimal that's between 0 and 1. Now x, we can substitute n equals absolute value, or the n equals the floor of x here, and then add n to both sides to get that x is equal to n plus a fractional part of x. Now let's consider the floor of x plus the floor of m minus x. We can substitute x equals n plus the fractional part of x from the line below to get the floor of n plus fractional part of x plus the floor of m minus n minus fractional part of x. Because m and n are integers, we can bring out the m and the n from the floor. So now we can simplify. So you have n here, m minus 1. If I add those together, I end up with m. And so what's left inside the floor function is the fractional part of x, and then plus a fractional part, or negative 1 times the fractional part of x. So then what we have to do is just simplify this, and we're done. So let's look at first the fractional part of x. We know that the fractional part of x is going to be between 0 and 1. And the way to think about this is like, okay, if it's between 0 and 1, that's like 0.1. And if I take the floor of that, that's just going to be 0. Now if I multiply this by a negative, the inequality flips, and we have 0 greater than negative fractional part of x greater than negative 1. And so think of that as like negative 0.1. And when I take the floor of that, that's just negative 1. So now, if we look back over here, the floor of fractional part of x is 0. The floor of negative partial of x is negative 1. So that just simplifies to just m minus 1. And so that completes a proof.